Okay.
Yeah?
It's okay, you can start.
Okay, thanks. Hello everyone, my name is Alonso and today I'm going to present my master thesis that is about synchronization in neural mass models. So first of all, I'm going to explain the motivations of our work, why we study synchronization and why we study it from the neural mass model point of view, and then I will try also to explain and will observe synchronization, and not only that, but also anticipated synchronization, that is a special regime of synchronization. Okay, so why synchronization is that important? We all know that our brain is built by billions of neurons that are connected to each other via synapses, that we have like 10,000 synapses more than billions in our brain, and overall, there's a huge neural network that we're trying to understand. I believe that it's giving rise to high-level performing tasks such as cognition and reasoning. We still don't know how this can happen, but some isolated mechanisms have been reported to be very helpful in order to achieve this kind of phenomena. And one of those isolated mechanisms is synchronization. Why we use a neural mass model is because when we measure synchronization in experiments, we used to do it with electroencephalogram techniques that measure the activity of a whole cortical column. Then, if we try to simulate this data, it's very computationally inefficient to do it from a microscopic point of view, and then we need to explain what a neural mass is. First, I will explain how a neuron works, how it can produce spikes, then how we can model it with equations, and then how from these equations we can extrapolate the behavior of a whole cortical column. So a neuron is a cell. Cell has a membrane that is a biphasic layer that has sodium-potassium pumps and voltage-dependent ion channels. And in its resting state, the configuration is this one, where there's an accumulation of positive charge in the outside of the cell and an accumulation of negative charge inside the cell. This produces a difference of potential that is around minus 17 millivolts, and the permeability of those ion channels is almost zero at this moment. But what happens if the neuron is perturbed? If the perturbation is small, the neuron goes back to its resting state, producing no spikes. But if the perturbation is large enough and the membrane potential reaches minus 55 millivolts more or less, then sodium channels open and there is a current of sodium from outside to inside the cell. This produces a spike, and and the neuron depolarizes. When the spike is almost at its maximum, what happens is that the neuron reaches the potential needed in order to open potassium ion channels, and then that depolarizes the neuron. Then, because of the potassium channels are slow, then we have here this hyperpolarized region, and then sodium-potassium pumps manage in order to have the neuron again in the initial state with the configuration of potassium ions inside and sodium ions outside. Okay, so this is very similar to an electrical circuit where the membrane of the neuron acts as a capacitor, and that we model in the following way. And when some potential threshold is reached, then the flow of currents start to take place here. This is something we already know how to model and how to describe mathematically. And in order to be a little more precise, we will need to take into account also the conductances of the potassium and the calcium that are in charge of repolarizing and depolarize the neuron. This ends up giving rise to Morris-Lecker equations, where here we have the classical potential dependence in time of the circuit, and here we have those parameters that account for the potassium current is more slow and is modeled with a re-escalating time and also a differential equation. This model, although it's very simple, provides us with some very special regimes. For example, just varying the conductance of calcium. Here for 1 or 0.5, we have different examples of traces that also have a different kind of behavior. For example, here above, below, interspheric frequency versus intensity plots, what we can see is that starting from low frequencies, from low intensities, the neuron does not fire, and once we reach an intensity threshold, the neuron starts to fire for arbitrarily low frequencies. This is characteristic of a class 1 excitable system. However, in the other case, what we have is a discontinuity here, and the neuron starts to fire at a given frequency. This is a characteristic of class 2 excitable systems. If we want to build a microscopic description of this neuron, if we want to build a neural network, then we'll have to take into account that we have a lot of neurons. We'll have to integrate to Morris-Decker equations from each one of them. We'll have to compute calcium ion probabilities, calcium probabilities and potassium probabilities for having the voltage-dependent ion channels opened. And also the model has been evolving through time. So we will need also to take into account the model is still very complex and displays a lot of high nonlinear behavior, spatiotemporal patterns, and can consider the topology of the network. This is computationally very inefficient, and maybe it's not what we should be doing when we are trying to simulate the behavior of a whole cortical column that accounts for thousands of neurons. So as we believe that it's not the behavior of an individual neuron, the one that is important, but the interactions of all of them, the one that gives the nature, the special nature of the brain and the special behavior. So what it was proposed later was to model a large populations of neurons with a population density approach. In this kind of approach, what is considered is that each neuron follows a Langevin equation, and as we have a lot of neurons, they populate the phase space following a probability distribution function that evolves through time with a Fokker-Planck equation. This here, but I just want to explain because I think that are very important to be, it's very important to be aware of them. So the first one is that we will consider the synaptic input intensity and uncorrelated, and yes, the intensity input uncorrelated, and with that we will be able to describe the evolution of the probability in time with a Chapman-Kolmogorov equation, expansion, that we will truncate at the second moment. And by doing that, we will need to calculate the average input of intensity in the neurons. And in order to do that, we will have to use a mean field approximation that will average over the coupling constants between neurons and also between the activity of the neurons. Once we have that, we arrive to this Fokker-Planck formalism, but we still don't know how to integrate it. And what is proposed in neural mass models is to come for a very simple solution that is simply considering that the probability distribution function is a Dirac's delta. Diversity, and we have very different neurons. And we will simulate excitatory pyramidal neurons and inhibitory pyramidal neurons. Those different populations of neurons will interact and will cause an effect to the other population. And this effect will be also approximated using a mean field, using a mean field where we will account that the mean activity of the excitatory columns is proportional. It affects in a proportional way the activity of the inhibitory and the other way around also. Okay, so after all these approximations, we arrive to the Larter-Brexper model, where B stands for the average membrane potential of excitatory cells, Z stands for the average membrane potential of inhibitory cells, and W is still the recovery variable accounting for the probability of having the potassium ions activated. So here we have mostly it is built with excitatory neurons, and the inhibitory neurons are less and are distributed along this fourth layer. This helps us model this very simplified circuitry of how the excitatory and the inhibitory neurons interact. What we will consider is that there are a lot of excitatory cells and that those affect each other, and then this will be represented here with this self-feedback loop, and they also affect inhibitory neurons, and this is represented here with this connection. However, inhibitory neurons, they don't affect each other as they are considered to be surrounded by excitatory ones, and they will only affect excitatory neurons. So with this very simplified model, with all the approximations and everything, and reproduce very different activity. For example, here we can see that the system has only one stable fixed point, while here it has a limit cycle behavior, and here it can even display kind of chaotic behavior. By the way, this will be the regime where we will find synchronization, and well, in order to see if two neural masses synchronize, what we will do is couple them in the most simple way we can imagine, that is an excitatory coupling and unidirectional. This coupling defines that this neural mass will be a master neural mass and this neural mass will be a slave. What we expect to see in this case is that once the master neural mass produces a spike, a perturbation is transmitted through this synapses or coupling and arrives to the slave, and then as the slave is perturbed, it also produces a spike. If the system is synchronized, this time between interspikes will be would be accotated and will be equal to some constant, more or less. And well, if we include the perturbation of the master neural mass in the slave, this only introduces two couplings here in our equations that are proportional to the coupling strength and to the average firing rate of the master neural mass. Sorry. This produces synchronization. This is an example of two neural masses coupled with a strength constant of 0.2. What we can see here is that the time between the two spikes is very small. We can plot an histogram of this interspike time for different values of the calcium conductance and the coupling strength, and we can see that the system is 0.1 and producing this highly centered distribution here. And in the other case, however, for values of the calcium conductance of 2.1, the system hardly synchronizes. The distribution of time between spikes is it's not centered, and we could only see one regime of synchronization here for the coupling strength equaling 0.3. However, this is not a very interesting regime for us, because for each spike sent by the master, the slave neural mass displays two spikes, and also this kind of synchronization was not very stable and was not interesting. So what is clear is that varying this parameter, the system undergoes several changes in its behavior. And if one looks at the literature, with what we have found is that there was a paper from Emerson in like a decade ago or so, where they were relating the class of excitability of the system with the ability to synchronize. Is that indeed for the system that easily synchronizes, the class of excitability is type 2, and for the system that hardly synchronizes, the class of excitability is type 1. This seems to be a type 2 excitability, and if we do a continuation plot starting from high and low values of the intensity, we can see here an hysteresis cycle, very typical from subcritical hot bifurcations. And well, here in the other way, what we can see is a logarithmic divergence that is very typical from homoclinic bifurcations. So our results agree with the ones that the theory of elements would predict. Okay, so we do not only want to prove that the system has a synchronized behavior, but also that we want to see if it can displace anticipated synchronization. The typical scheme in order to prove that, well, what is anticipated synchronization is that although the master is sending the information to the slave, then the slave is able to spike and lead the master. This happens if the slave is submitted to a self-inhibitory feedback loop. This self-inhibitory feedback loop can be modeled in biological systems and as an inhibitory interneuron that is bidirectionally coupled with the slave. What we do in our neural mass, if we have this unidirectional coupling here, is the following. So we don't have to add here any inhibitory self-feedback loop because we are already accounting from inhibitory neurons inside the neural mass. So what we plan to do is just to increase this coupling connectivity, so increase the effect the inhibitory interneurons have in that we are able to reproduce anticipated synchronization. Okay, so those are the plots of the distribution of times, and we can see here that the system reproduces direct synchronization for values of the internal connectivity constants between 1 and 2, while if we increase above 2 the internal connectivity constant here, those times shift to the right and are negative, and then this means that as we can see here in this transition, that the slave starts to fire before the master. This is an example for unidirectional coupling, but we can also try this considering bidirectional coupling, as some regions of the brain are connected using this kind of coupling also. We will proceed in the same way. We will increase the internal connectivity constant of neurons to excitatory neurons. What we observe is the same. We observe that for internal connectivity strength larger than 2, the system also displays anticipated synchronization. However, in the case of unidirectional coupling. Those are some plots of the average time in function of the internal connectivity, and what we have seen also is that varying the internal connectivity is not the only way to display anticipated synchronization, but also varying the intensity applied to the slave neural mass also ends up displaying a small regime of anticipated synchronization here. Those are our main results. And well, finally, I would like to conclude saying that we have gained some insight in neural mass models, but we know that they can reproduce not only synchronization but also anticipated synchronization. We find different ways to reproduce anticipated synchronization, although we don't know which one is responsible of having this phenomena in the brain. Maybe it's a combination of several of them. And well, I think that some ideas for further work would be to study synchronization in other type of bifurcation. Find some difficulties in having a synchronized system or not. Don't know, it would be interesting to test. And also take into advantage that neural mass models are very computationally very fast, and then we could build some kind of a spatial structure simulating maybe some areas of the brain where we could test if the synchronization and anticipated synchronization is still stable. So here's some bibliography if you want to check some of these ideas. Well, thank you a lot for listening, and if you have any questions,
well, now the jury will make some questions. First of all, thank you very much for being almost perfect on time. 21 minutes or something like that. It's perfect. So now we'll ask you some questions. We'll start with Dr. Jose Soriano.
Thank you, ma'am. And thank you, ma'am, for the presentation. and for the work you have done.
You're welcome.
Nice everything. I have a number of questions. I will start with the panel.